I don't know. What are we going to do? I'm going to try not to go too fast. But I'd like to get through this to the first assignment slide in the next part. So we shall see. Okay, are we ready? Got my calculator ready in case I want to tap anything into it. So in this part, we talked about density. Density is just like a nice little division. Density of something is always, you isolated something like we did in lab. We find out the mass of that object. We calculate the volume of that object. Density is a ratio of mass divided by volume. Okay. The other thing, I'll get at the door.
Yeah, it just like
it does. She projects. In a good way.
Yeah, it's a good thing.
Yeah. We talked about mixtures, so matter is either a pure substance or a mixture. And if it's a mixture, one way to talk about kind of how much each component is there is its mass percent. Mass percent of a component. You're already kind of familiar with how this works. Weight percent, we do percents all the time, but this is mass percent of a component. So if we have a certain amount of, like if we say that your mixture is 21% by weight of component A. Now I'm going to need you to be able to, what we say, unpack that. And this is how you unpack it. You're going to have to be able to unpack weight percents. And what that would mean is you have 21 grams of A in 100 grams of mixture. I'll just put MIX for mixture. That's what that means.
Where did you get 21?
Because I just said it was 21%. Yep, I just made it up. Now we've been talking about counting significant figures. I'm hoping that you'll buy this. This actually unpacking is a by definition. By DEF for definition. So that's to say that there's no uncertainty in the 100, but there is uncertainty in the 21. So actually we have two, SF stands over, of course, sig figs. We have two significant figures, as I've kind of randomly picked 21% A. Okay, that's unpacking it. But usually you don't have 100 grams of mixture. Usually you just have some sort of, like you have 35 grams of mixture and somehow you tease out component A, right? So this is, if you isolate, this is how you calculate weight percent. Basically, you isolate a certain mass of your mixture, okay? You take the component of interest out, and then you basically divide, you take the mass of what your component divided by the total mass of your mixture. Okay. And I'm going to kind of throw something at you. You can go ahead and add it to the slide if you want to. But I'm going to go ahead and circle or try to kind of put brackets around that first ratio. And if you don't do times 100%, you have what's called mass fraction. To kind of show what I mean is if I go ahead and take that ratio times 100%, then I have mass percent. Okay, that's kind of how that works. Okay. Mass fraction. What is mass fraction? Well, you calculate it kind of the way you calculate mass percent, but you don't multiply by 100%. So if you want to add something here, you say you, let's see. Oh, wait a minute. Two things. By definition, DEFN, by definition. Okay. If somebody gives you a mass fraction, that means the fraction of a gram, so I'll put grams of component A, it will be a fraction of a gram per 1 gram of mixture. That's what it means. And how do you calculate it? Basically, you take the grams, number of grams of A, and you divide it by number of grams of mixture. And you don't multiply by 100%. That's it, mass fraction. Okay? So do you guys buy this? What did I say, 27? How much? I just pulled that number, 21. Okay, do you guys buy this in that thing we talked about before? So for instance, in the previous example, that would be 0.21 mass fraction of component A. Is that by, it goes back and forth by a factor of 100, basically. You okay with that?
Fraction, what are you saying, mass fraction A?
Component A, yeah.
So like, if you have a mixture of trash and it weighs 10 pounds,
Mhm.
and 1 pound of it is pop cans, 1/10, the fraction would be 1/10,
Yep,
would be the last fraction of that?
yep.
Okay.
So it'd be one, yep,
Yeah.
yep. And then what would the percent be?
10%.
Times 100 would be 10%, yep.
And then that 10%, that would be the mass percent.
Yes,
Okay.
yep. Did you catch that? Okay. Very good, that's a good example.
Cross canceling of the units when you do that, right?
Right, in fact, I have a slide coming up, and what she's saying is, in the case of, well, both cases, your grams will cancel out, your pounds will cancel out, and that actually makes it essentially unitless. Yeah. So, bless you. Okay, cool. Okay, so we'll work a problem, and, you know, this might be overkill, but I find comfort in drawing a picture, so I'm going to go ahead and draw a picture of this aqueous solution. So there's my beaker, and to it I'm going to put, my component of interest is 5.42 grams. And then it looks like I'm going to go ahead and add, I'm going to put SUC for sucrose. And then I'm going to add 28.72 grams of H2O. And the question we have is, what is the mass fraction of sucrose? And then also, what is the mass percent of sucrose? So those two questions. So of course, the mixture has two components, this 5.42 grams and the 28.72 grams. So basically, I would come up with the mass of the mixture. The mass of the mixture, in this case, I'll just go ahead and tag it with solution. The mass of the solution is the mass of sucrose plus the mass of the water. Now again, we don't do much addition, but since we're adding, how are we going to round? Decimal places, exactly. So we're going to keep those 2 digits after the decimal. This is actually a good example where if we were multiplying these numbers, we'd round according to significant figures, but we're not. We're adding, we're going to keep 2 digits. Okay, then let's not make it harder than it is, right? Our mass fraction of sucrose then is simply the mass of the sucrose, 5.42 grams, divided by the total mass, 34.14 grams. Since we're dividing now, we round according to sig figs, exactly. So I got 0.159 mass fraction. Does this make sense? Your mass fraction will always be 1 or less, right? So.
And is it a pretty constant to put, like this had the sucrose on the top and the solution on the bottom, is that typical for?
The typical pattern? I would say yes. Yep. Because this is the component, like our component A, and this is our mixture.
Mixture's probably always a great number.
This
Yep.
is going to be a really dumb question, but for years and years I thought, when sugar's dissolved in water, is it actually equal to the two amounts? But it is.
The volume, or the mass?
Yeah, okay.
Which
okay,
one? Because the volumes sometimes are not additive, but
okay,
masses should be.
Okay.
Yep. I don't know if you've heard I had a student, or teacher do it a long time ago. If you take water, I think this is right, if you take 500 milliliters of water and you add it to 500 milliliters of methanol, okay, and you add them together, you will get smaller volume than 1,000 milliliters. That's just because of how they mix and they form intermolecular bonds. But their masses would be additive. So, okay, so that's it. So if somebody says I have a sucrose solution, it's 0.159 mass fraction, you need to be able to unpack that. That means I have 0.159 grams of sucrose in 1 gram of mixture or solution. Mixture and solution are synonymous in this case. That's by definition. And again, there's no uncertainty with that one because that's by definition. Okay. So the problem asked mass fraction, which we got 0.159, and it also asked mass percent. So what's the mass percent? Multiply by 100, exactly. Exactly. So for the same sucrose solution, and I know I say to show all of your work, but I don't know how I would I would almost just intuitively go, if I got the 0.159, I'd go 15.9% by weight.
You've been using grams all throughout this so far, but it'd be the exact same if you were going by like milliliters or anything like that, right?
Yep.
It's not just grams.
And if you were going milliliters, that would be, that wouldn't be mass fraction, that would be volume fraction and
Okay.
volume percent.
Okay, duh.
Yep,
Okay.
so you could do milliliters, but it would
Be
be,
volume percent.
yeah,
Okay.
yep.
Is it a different formulas or?
Nope. We do run into the problem where if there's new types of intermolecular bonds are formed, we could actually get, our volumes wouldn't be additive though. Masses are
Because of what
always,
you guys were just talking
yeah,
about.
masses are always additive. Volumes, not so much. Volumes of gases should be additive. Volumes of liquids, not always.
That's cool.
Yeah, I think so. I'm not the only one. I do think that's neat. Okay, cool. So we're going to take a look at these. I have screenshots of these problems. The first two are density problems, and the last two are percent problems. I'm not real sold on the 63, 64, the percent problems. It's just what we had to deal with. I think I saved them. There you are. Okay.
Was this one, did we have a salmon today?
No.
Oh, okay, I was freaking.
Was there? No, there wasn't anything to.
Because we
It's
didn't
like
go all the way through
freak out
this.
day.
Right.
Freaking out all the time. Freaking out all the time.
Not in this class, but, so this one, 47, looks pretty straightforward. You can see if you're like me, I don't like the words, I like the numbers. So I see the 1088 grams. I see the 2.18 liters, and density is a ratio of mass to volume, and actually we're after the density. So I could go ahead and knock out the density. The catch here is that the units they want it in are not grams per liter. The units that they want grams per milliliter. So honestly, if you want to just stop at grams per liter, I'm fine. But if you want to go ahead and take it to grams per milliliter, you have a couple of options. You can just eyeball that, and probably as you've gone maybe through this class before, you know the relationship between that 2.18 liters and milliliters. You move the decimal place over, what, 3 places? Yep. And that will work for this problem, but after, it won't work late next week, and I'll kind of show you why. So instead, if you want to get used to doing this, feel free. Notice what I did in blue down here is simply the same. I started the problem the same way. I inserted one term. That one term is the relationship between liters and milliliters. And the cool thing is, and we're going to talk about that momentarily, The cool thing that happens here now is that liters in the term I inserted will cancel with liters in my first term, and I'll be left with units of milliliters. So now my units are grams per milliliter, which is what I wanted. Isn't that
Does it
fun?
change? I guess it wouldn't change anything if I would have wrote 1,000 milliliters over 1 liter times 2.8 liter over.
Yeah, because what you're kind of describing is the inverse, and you should, I think you'll get milliliters per grams.
Nursing, they use it the other way.
Oh.
Like, whatever you're searching for, you start with,
Okay.
and then cancel.
Oh, yeah, that is just the opposite. In this case, you start with what you're given and end with what you're trying to get to.
Would it be the same? The same answer?
Try it. I don't know if I'm entirely following you, but.
I'll try it. I'll just
Yeah.
answer it.
But what I tell students is to work chemistry problems, if you really focus on the units, get the units, because it says what is the density in grams per milliliter. So grams per milliliter, that's what we want.
They do all this with the conversions of medications and pharmacology.
Okay,
That's like,
interesting.
and they have a method and like.
And they use
all
kind of
the
the factor
time.
label, let things cancel and everything.
Liter, milliliter, liters, all that stuff.
Good.
So,
You just might need
hoping
to
it's
switch
the
it
same.
around. We'll go with that.
Maybe we'll try to change that.
We'll go with that. So the second density problem has kind of a similar deal. Okay, so
That
you're after,
1,000 would be considered exact.
what's that? Yes.
Okay.
And
Don't
this,
round it.
this
this-
term right here, this is an exact relationship. So we don't round, we don't limit our sig figs to that. So to me, I'm thinking, how many sig figs you think you gotta round it to?
3.
I'm liking 3.
Sorry, I didn't mean to interrupt you.
You're fine.
Is that an E or a P?
Is that a what?
An E thing, or is it more of a P thing?
It's more of a P thing. It's a row. It looks like a cursive P, I think. What were you gonna say, Mike?
I was just saying, so.
Yeah, it's a row.
I gotta learn.
Yeah. But it kind of, instead of, you kind of start, you kind of start with the circle part and then go out to the stem part. So you kind of go like this. You go like this.
And then you drop that.
What's that?
Kind of like they put the letter P in italics.
Yeah, it does look like an italics P. So the other one, you notice we have kilograms per liter. And again, we want grams per liter. So what's the relationship between kilograms and grams?
1,000 grams.
1,000
equals
again,
1
yeah.
kilogram.
So notice that and to me, if you want to go ahead and do that, you can. Just leave it in kilograms per liter. I'm fine with that. But if you want to go ahead and fix it, oh, that's right. And also at once instead of liter, milliliters. So if you want to go ahead and fix it, actually, I have 2 terms down here. I guess they're in purple. And I will take this as a PDF. I know I see you guys, some of you guys taking notes. I'll take this as a PDF and push it out. I always take my hints and push them out under Twitter. So this document will appear hopefully shortly after class under Twitter. And if I don't, sometimes when, Mrs. Snipes, where's the hints? So I'm like, oh, okay. Okay, so this document will appear. These are my hints for the problems. So I'm kind of a little bit open for this problem. And when you do that, by the way, well, did I already say? Yeah, the units cancel and you get grams per milliliter. Now, my only hints, I have a hint for question number 64. I told you that I'm not real thrilled about this problem. Instead of dealing with something like mass, weight percent, it deals with basically a population of students and their grade distributions. So I'm not real thrilled with it. Just do your best. You'll get it fine if you, okay? But I did down here for 64 remind you one of the things that I said is I want you to unpack the percents and try to use them and have units cancel that will cancel. So
when you get 1.5 students, you want it discrete, rolled up to 2 students.
exactly. That's
Okay.
one of the things I don't like because like it's exactly what she's saying. I don't like the whole rounding thing because you can't have 1.5 students. So you got to round to the nearest student, which kind of drives me nuts because I just don't like it. But I don't not like it enough to try to come up with another problem. Okay? So, all right. So let's go ahead and go on to part 3. Yeah, there's some problems, and that's one of them. When I graded, I'm like, oh, excuse me, part 4. We did part 3. When I graded, I'm kind of like, I don't care what they put. Some things I do care more. Okay. So some of these are review slides, the first few, because we've already kind of talked about this. Now, which ones are you supposed to commit to memory? Do you guys remember? Kilo is 1.
A mega.
I didn't say mega. Not all of them.
Micro.
Nano.
Micro, centi, milli, and did I say nano too?
One of those two.
Because I say 4 or 5, and that's 5.
I feel
So
like Pico in my other classes we haven't really had to.
yes, I agree. Pico's kind of like, Nano, I like it because like wavelengths of light are kind of nano. So yeah. So memorize these. Memorize 3 little ones and 1 big one. Centi, milli, micro, nano, and kilo. Okay. And then this little bit, which of these you're supposed to memorize?
1 inch equals 2.
Probably all of it.
No, not all of them. Just the first one. Because it's chemistry. We don't memorize things like that.
See, when you do this stuff, it makes us love you. Because if you just put links up there, we just wouldn't feel it.
Oh.
When we see the things that we don't have to do, that's where the.
Oh, okay. We'll go with that. Now, what does exact mean? How?
Definition.
It's a by definition?
Exact certainty.
Exact certainty? What were we going to say, Mike?
I would say that.
Yeah. So we don't have
Absolute.
absolute, yep. Those other 2 are approximate. And you're supposed to memorize this one? Yes. So this is the volume thing. Now this is within the metric system. 1 milliliter is exactly equal to 1 cubic centimeter within the metric system. These are kind of fun. I have a term called, well, I didn't make it up. It's called the imperial bridge. Okay, but can you see where these are all going between English and metric? Okay, so the English metric counterpart. And before I leave this slide, if you're using, for instance, the volume 1 gallon is approximately equal to 3.785 liters, you have to go with 4 sig figs. And this one here is generally exact. That's just kind of how that works. Similarly here, this one is exact, or no uncertainty brought here, and this would be 4 sig figs. Okay, cool.
Why do we say approximately?
What's that? Why do we say approximately?
Yes, if it's exact.
Oh, the way we read that, if we say if you exactly, for instance, I know it feels kind of weird, if you exactly precisely have 1 gallon in English units, you have the approximate amount in the metric system of 3.785 liters. So we're sitting 1 in stone, and the other one's approximate. That's the way I think of it. Okay.
I'll work on that.
Okay. So the problem that we did a little bit ago with density that's going to be due, okay? Remember the terms I added and let things cancel? That actually is going to be explained right here. So when working problems in physical science, I think this really helps to use the factor label method. And it sounds like what nurses kind of do, except we do it backwards. Okay. I don't know. But the label part just means units. And to me, the factor part, you guys remember on the first day of class, I put like 3 ratios up here, and you had things canceled, okay? You factored out, and if the term appeared, you let it cancel. That's the factoring part. So factor label. Label are units, and we're going to let them cancel out. So one of the things, and I call this no naked numbers, thou shalt have no naked numbers. I know we've had a few to start because we're just kind of getting our feet wet with numbers. But you always have to have units after the number. So we've run into actually a few of them on that yellow slide, the 3 where we had, 1 inch is exactly what 2.54 centimeters, those are equivalency statements. When I go like that, that's an equivalency statement, okay? So we are going to use equivalency statements to get us down the road using the factor label method. We are going to make, I know it says unit factors or conversion factors, but basically we're going to take an equivalency statement and we're going to make it into a ratio. So we're going to take this and make it into a ratio. Equivalency statement, make it into a conversion factor to get us down the road where we want to be. And then we're going to take that conversion factor, that unit factor, and we're going to use it, maybe string up more than one, to get from where we are, where we start with, to where we want to be. And as long as you focus on units all the way through, what you have, where you want to be, not too bad, okay? Factor label method of approach to working problems. Okay, so let's start within the English system. So if I have 2.5 feet and I want to convert those to inches, 2 feet is how many inches? 24. A half a foot is how many inches? 6. So I take 24 plus 6, I got 30. You're done, right? That's it. Okay. Notice I went ahead, what does that decimal after the 0 and 30 mean? How many stick figures do I have there? 2. How many did I have in 2.5 feet? 2. So that's not like accident. I mean, I'm trying to be consistent there. Now let's do that same problem converting 2.5 feet to inches using the method I just described. Okay. So to use the factor label method, what you do is you look at the units you have, in this case feet, you look at the units you want to get to, in this case inches, and if there is an equivalency statement that links the two, you go ahead and write that down. This is the flat equivalency statement. And from every equivalency statement, you can come up with 2 conversion factors. Okay? Now, one of the things, I'm not a math teacher, but one of the things we know that we can do about it with equalities is as long as we do the same thing to both sides, that's legit. So let's divide both sides by 1 foot. We have 12 inches divided by 1 foot, 1 foot divided by 1 foot. Obviously, what's 1 foot divided by 1 foot? It is 1, exactly. Okay. So if this quantity is 1, then this quantity is also 1. Does that make sense? Okay. So what happens if you take 1 times anything? It's the same thing. So we have made a conversion factor, a unit factor, that basically, if we insert that anywhere in our problem and we're multiplying by that, no harm, no foul. Well, let's take the same equivalency statement and now divide both sides by 12 inches. So 12 inches divided by 12 inches, of course, is 1. 1 foot divided by 12 inches then must also be 1. Okay. So any equivalency statement can end up actually with 2 ratios, 2 conversion factors. Which one are you going to use? Whichever one you need to use. Okay. So I kind of do it like, it's almost like the Pee Wee Herman. You do it like that, okay? I know. I practiced that, Okay. So what I tell students is your first term is going to be the thing you want to convert, which the thing we want to convert is 2.5 feet. So I would put 2.5 feet, I almost started to draw that, but I thought I have it on the slide. I usually put that over 1. And the reason I put that over 1 is to emphasize my units are in the numerator. So you guys have it on the previous slide.
Sorry.
You're fine. You guys have it on the previous slide, the 2 ratios. The first ratio, was, what's the first ratio?
Are you talking about this?
Yep. The first ratio, you guys are great. First ratio is 12 inches over 1 foot. The other one was what we call the inverse, 1 foot over 12 inches. How many people think we're going to use, let me say, make sure we're all on the same page here. I can't remember which this was. Or the inverse. And those are both 1. So if we call this A and this B, how many people think we're going to use A to make units of feet cancel? How many people think we're going to use B to make units of feet cancel? That was my point.
You can do it either way, right?
What's that?
You can do it either way.
Well, and I have a slide to show you. So if most people thought, well,
1 to inches.
no, you can't use either one, and I'll show you why. We have to use B, and the reason we use B,
No, that's what I used anyway.
what's that?
That's what I used anyway.
Well, why did you use it?
Because I've always said, doesn't mean I'll continue, I've always set the equation with whatever I'm looking for first to put on the top. So if I'm looking for inches, I
Ah,
put inches on the top and then I go from there.
okay,
And that's been a great rule of thumb for me.
okay. Well, as long as what, and these might get even a little more complicated, because sometimes it's not just one term, and that still might work. That still might work. So, and actually, I have had students before that I'll show, maybe even 4 terms multiplied together, and I'll look at their work, and it's exactly backward.
That's
So,
really something from college.
That's probably,
You use,
Okay.
you use all kinds of,
it's like a little puzzle to kind of figure out how to get it done.
it is, and it's just trying to get from point A to point D, and then
Yep,
how you
Okay.
keep converting.
it sounds like that's going to work for you,
I hope so.
Emily.
Because it is fun. And I need more practice.
But we couldn't have used, and I have a slide to kind of show you that. We had to use this one, whichever method you did, Emily's method or, yeah. So feet cancel, units of inches are left. Now, I focus on units before I focus on numbers. So only when my units work do I worry about numbers at all. Okay. So our calculator would display actually the number 30. But we know we need, if I put 30, how many sig figs are there? Just one. Just one. But 30 with a decimal, then I've got 2. Yep. So this is what I was trying to say. Say you chose A, this is what it looks like. You have 1 foot times 1 foot over 12 inches. And then you end up with units are feet squared per inch. And that's all right. Okay? Cool. Let's do a few more. Let's do one that requires us to go from centimeters, which is metric, to inches, which is English. And sometimes I kind of show kind of from left to right how we're going to do it. So here's our strategy from centimeters to inches. And over that arrow, I'm going to say, how do you get, what's the equivalency statement that links those two? 2.54. Yeah, 1 inch is exactly equal to 2.54 centimeters. Sometimes I get it mixed up. But then I have to think, well, how big is a centimeter? How big is an inch? 1 inch is exactly equal to 2.54 centimeters. Okay, so that's our flat equivalency statement. So to work the problem then, I would start with the centimeters over 1 that I want to convert. I know it doesn't have it over 1 in my notes, but I'd put 5.52 centimeters over 1. Or if you're Emily, you would start with the, okay. And then doing it my way, what would this ratio look like?
1 inch over 2.5%.
Yep, 1 inch over 2.54 centimeters. So our centimeters would cancel. That's awesome. And I need to round it to how many sig figs? 3. But remember, we're not rounding it to 3 that The 3 sig figs here bring no uncertainty, so that's not limiting us. But this is limiting us. Yep, I'm liking it. And the units would be inches. I got 2.17 inch. Okay? Now, in both of those cases, we already had an equivalency statement linking what we knew and where we wanted to get. We already had just, okay. So, but this is an example of, if you go back a few slides, remember I gave you the relationship between pounds and grams, okay? And if that's the only thing I gave you on the test, you would have to actually add something. I know from pounds to grams. So actually, if I went ounces to pounds and then pounds to grams, I could do that. What's the and I would throw this on a test, but maybe homework because you can Google it. Do you remember the whole ounces pounds thing?
16.
Yeah, 16 exactly. Is that exact? Yes. Okay, so that's how I'm going to work it. So I'm going to go from ounces, like I said, to pounds, and then pounds to grams. So yeah, so we got 16 ounces is exactly equal to 1 pound by definition. And then a few slides ago, that little box that you don't have to memorize, well, some of you think you should. No, I'm just kidding. Kind of between the metric English system, we have 1 pound is approximately equal to 453.6 grams. So in this case, I'm actually going to have 2 conversion factors to get from ounces to grams. So what's my first term going to be in the way I usually work them?
2.75 ounces over 1.
Yep, 2.75 ounces over 1. Perfect. Now I want ounces to cancel. I want ounces to cancel, and I want to be left with pounds. So how can I use that equivalency statement to get there?
1 pound over 16 ounces?
I'm liking it. 1 pound over 16 ounces. Very good. My ounces will cancel. And now the next step is I want to go to grams. How can I use that to get to grams? What would be that next term? I want pounds to cancel. I'll be left with grams.
453.6
Yep, 453.6 grams over 1 pound. That's exactly right. So again, I just have been focusing, I've been carrying the numbers along, but just focusing mostly on units. So I have units of grams. So let's see a show of fingers. Rounding, rounding, rounding. How do I need to round this?
I think it's 4.
Who said 3? Why did you say 3?
The first number is 2.
Yep, it is 3 actually. So the way,
The previous slide, the 453.6, those are uncertain.
yes, you're right. Look, so I'm going to do this. So you're right. I'm going to go 4 here. I'm going to go 3 here. Now, is there any uncertainty? No. Okay. And it's always fewest. So it's always fewest. So that's why it's 3. Yep. So I got 78.0 grams. Sometimes my slides are wrong. So let me know if I think that one's right, though.
It's 77.9, so, I mean, it has to be rounded up, so.
Oh, good, yeah, because the next digit's a, yep. Very good. What do you think? Okay? Questions? Okay. Let's do this one.
What did, I'm sorry.
Yeah.
Can you show me the answer to that again?
Sure. 78.0, 3 sig figs. And I was looking at Rhonda's calculator up here, and actually you get 77.9625, yeah. And so 3 sig figs means you have to truncate at the 10th place, and since it's a 6, you round that up.
Okay, good.
Yep.
Just wanna make sure.
So for this one, we're gonna go ahead, if you look a few slides ago, I said the approximate relationship between a liter and, was it a quart? Gallon.
Gallon.
Yeah, a liter and a gallon, so we're gonna use that one, I think. Dang, so we have 275 milliliters, trying to get to cups. So, we can go from milliliters to liters. What's the relationship there?
Times 1,000.
1,000, yep. And then we can go from liters to gallons. We can go from gallons to cups. So you told me 1,000, so 1,000 milliliters is exactly equal to 1 liter. That will get us from milliliters to liters. And then the one a few slides ago, I gave you the approximate relationship between liters and gallons is 3.785. So 3.785 liters is approximately, is equal to 1 gallon. Does anybody know the whole gallon cup thing?
What would be
I'd have to look it
Like-
up.
8 cups and a quart, and there's how many quarts? 2 quarts and a.
Yeah, so that's not so bad. 16, very good. 16 cups in a gallon. Now, that's the sort of thing I probably wouldn't give you on a test, because I don't like that sort of thing. But this is how we're gonna work it. So what's our first term gonna be?
Don't ask me, I'll give you the opposite.
Yeah.
But I can answer yours just by that, it'd be your milliliters to liters.
Milliliters that you wanna convert, yep.
Although I'm using cups.
You
As long as it's
would,
okay
yeah.
with you.
Yeah, that's fine.
Okay.
275 milliliters over 1.
Yes.
Times 1,000 over 1 for liters to, no, is it the other way around?
It is the other way around, because why?
Because the milliliters have to cross
Yep.
cancel.
The second, Rhonda said, the second term is gonna be 1 liter, 1,000 milliliters. Yep, and then what's the third term gonna be?
1 gallon.
Yep, 1 gallon on the top, the liters in the bottom, and the value for that is 1 gallon over 3.785 liters. And usually I kind of cancel, I can see my bills aren't, but milliliters, you guys did this, milliliters will cancel, liters will cancel, we have gallons. So now, what are we gonna do? Yep, 16 cups over 1 gallon, I like it. Okay, so rounding wise, get your fingers ready. Rounding wise, how many sig figs? And why is it? It is 3. It is 3. So kind of left to right, let's take a look. Okay, so there is uncertainty in that first term. 3. Is there any uncertainty there? Nope. Is there uncertainty there? Yes. So I'm liking 4 for that. Is there any uncertainty there? Nope. So it's always fewest. So 3 wins out. All right. So I got 1.16 cups. Okay.
But like, I always thought you leave out conversion factors for counting the sig figs. But it seems like you do if they're,
Yeah, if there's
All the
uncertainty in
numbers.
the
Okay.
conversion factor from the equivalency statement, yes.
okay.
Yep. Some conversion factors, like Rhonda was saying, like this within the metric system, you leave them out for counting sig figs. But this right here, you can't, because it's not by definition, I mean, there's uncertainty in that equivalency statement. Okay. Okay, miles to kilometers, anybody? So again, you can kind of see that we've got a decimal after the 0 and 120, so of course that means I have 3 sig figs. So I'm going to go from miles directly to kilometers. And did I give you that equivalency? No. This is where I'm pretty sure Petrucci has this and a number of equivalency statements in the back. You don't have your textbook. Oh, she does. Shelby does. So yeah, if you look in the very back, like this, there's some nice sections right here. This blue is great. It gives some constants and some formulas, like the formula of the volume of the sphere, if you need it, hint, hint, for later. And so it also gives some equivalency statements. No, I don't see it there.
It might be in the front.
Might be
I
where?
think it's in the very front.
It's in the front? Did you say you thought it was in the front? I thought it used to be, but I don't see it there.
My notebook, I got it.
Yeah, Google.
Yeah. So I would give this to you. So let's work this problem. Oops, sorry.
So we go like kilometers to meters to mile.
In this case, I'm just gonna go miles to kilometers. Did you have it?
Kilometers.
Your physics book has it? Okay. I would give it to you on a test. So we're gonna just do it in one, fell swoop. So what does that ratio look like?
141 times 1.69 kilometers over 1 mile.
Yep. The second term is 1.609 kilometers over 1 mile. Miles cancel? How many sig figs? With confidence?
3.
3. Yes, very good. I got 193 kilometers. Yes, I think so. Skip the next slide. I think we're gonna skip that slide, skip this. We'll do this. We'll do the loon thing, but I'm gonna go straight to, I'm gonna go here. So let's take a look at these. There is some edit. I'm going to tell you as I show you them, ones that you don't have to do. How's that? I know, I like the sound of that. But unless I state otherwise, this set is also due on Wednesday. So let's take a look at them. Shall we? Where did I put them? You would think I would have put them right. Doesn't look right. No. Aha. I found them. Okay. So these are the first. Now, you have to show your work. You have to work the problems from now on out, showing all of your work. So, the hints are, I gave you a hint for C. Notice a hint for C, I've been showing kind of left to right how to work it. I would put, my first term for C would be 981 centimeters cubed over 1. Then I would go from centimeters cubed to milliliters, which that's a 1-to-1 relationship. And then I go from milliliters to liters, using the 1,000 milliliters equals 1 liter. Now remember, this I'm going to push out under Twitter. This will be a PDF, printable PDF. Now, for 27, don't worry about D. I went ahead and I'll push out a suggestion for D, but don't worry about D. It's optional if you want to. I'll put a little X over it so we're all kind of on the same page. Do it if you want. The rest of my hint for D goes like this. We'll be talking about this on Wednesday. That basically we have a 3-dimensional situation there. And I think the only other hint I gave you was for the next one for C. Now, notice what I like to do, if I'm going from millimeters, to centimeters, you probably would say, well, that's a factor of a 10th, or a factor of 10, however you want to look at it. But you'll notice when I work, if I were to work 28C, I would go back through the base unit. That's just what I do. Instead of going straight from millimeters to centimeters, I would go from millimeters to meters and meters to centimeters. I just think it's cleaner. Less likely to screw up. Then we have these. So 33 has a unit of a hand. You're like, really? What is that? But if you read it a few times, you're going to see that actually a hand links to the length of an inches, like this, an exact relationship. And then all I did on my hints was to kind of pull out, or I guess on my first hint, I went ahead and told you that I would go from hands to inches, inches to centimeters, centimeters to meters. That's how I would do it. Moving on to the next problem. Again, it's some weird sort of lengths just to kind of get you used to putting things together. Furlong, I'm not familiar with a furlong, but in the problem it tells you a furlong is equal to 1 mile. It talks about chains and furlongs, and they have a relationship of 10, and a link in a chain has a relationship of 100. So you'll read that in the problem. And then in the next one, 35, oh, go on. Okay, so, oops, sorry, go back. So 35, it says how fast a sprinter can run. He can run 100 yards in 9.3 seconds. And it asks you some questions. Actually, 35, I'm going to put the word wait next to it. You can work it if you want to, but I'll put wait, as in that won't be due until Friday. That'll make more sense when we cover the loon problem. How's that? So wait for 35. Don't do the D on the previous one. Let me take a look at the next one, see what we got. And for this one, dun, 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 and wait for this one. So wait for 35 and 36. But I'm going to go ahead, and it's just a pack, so my PDF will have these hints too. Any questions about that? So don't worry about 35 and 36. Okay. All righty then. What's that? I know. Yeah, I got 55 after, so.